Good afternoon, ladies and gentlemen. First talk after lunch is again Sean Harmer on OpenGL with Qt5. Thanks.
There we go. Good afternoon, everyone. Is everyone awake or getting very sleepy after eating big piles of dumplings? I am. I'm very tired. Right. So this afternoon we're going to talk about OpenGL and some of the ways in which it's used within Qt and how to integrate raw OpenGL scenes with QtQuick 2. So first of all, we'll have a quick tour through the support for OpenGL in Qt 5. So we'll cover some classes like OpenGL Context and see how that feeds through to the QPA backend if we get a chance. We'll maybe delay that to the end if needed. And things like OpenGL buffer objects, shader programs, frame buffer objects, all these little helpful tools that are just there to help you get your jobs done and make your lives easier. Then we'll have a look at integrating OpenGL scenes into QtQuick 2. There's a number of ways of doing this. We can render QtQuick 2 to frame buffer objects. We can render our scene to frame buffer objects. We can use underlays. We can use overlays. We can have custom items, all sorts of things. This afternoon, we'll probably just talk predominantly about using OpenGL scenes as underlays inside QtQuick 2 user interfaces. And then we'll have a quick talk about some of the stuff that is likely to appear in Qt in the future to help support further advancements in OpenGL. And if you've got any suggestions, I'll be more than happy to take them. So what is OpenGL? I guess most of you already know, since you're interested in OpenGL. It's a whole set of family of APIs for rendering 2D and 3D content. OpenGL doesn't care if it's 2D, it just forgets all the information about Z. So we can quite happily render 2D plots, graphs, images, 2D games, anything with OpenGL just as comfortably as we can with 3D. It's hugely flexible. It's a very, very generic API, especially the modern OpenGL. There's no more fixed functionality in terms of you have to specify this is vertices, this has to be colors, this has to be normals. You're now completely free to choose whatever your vertex attributes correspond to. So you can choose positions. If you have normals, great, supply them if you want to use them. If you have texture coordinates, that's also great. You can also supply temperature, density, whatever you care. Okay, really depends on your application. You don't have to stick with the old fixed functionality view of the world. It exposes huge amounts of computational power. When I say huge, to give you some sort of idea of scale, a modern day GPU will have potentially several thousands of cores. Okay, compare that to your brand new shiny desktop CPU, which has got maybe 8, 12 cores at best. As a result of that, modern OpenGL is all about how do we get all of our ducks in a line set up on the GPU, ready for us to pull the trigger with a draw command. Otherwise, if we're doing it the old style with OpenGL 1.x, then your GPU is going to be sitting there twiddling its thumbs, doing absolutely nothing most of the time. What's it good for? All these topics you can see up there and much more. The last topic, simulation, is especially important now with OpenGL 4.3, where we can also access compute shaders. So this allows us to run arbitrary calculations on the GPU, very similar to what OpenCL or QtDD allows us to do, but it doesn't incur the cost of a context change. So you can do simulations, output your results into a buffer object, and without ever transporting that back to the CPU side, do a rendering pass and display all your data using OpenGL. Okay. So let's have a look at our very basic example, which should already be open. Again, simple hello world triangle. Those of you who've been to the training or my earlier talk will have seen this already. But for those of you who haven't, we'll have a very quick run through just so we can see some of the Qt classes. So first off, in our main function, we have QGUI application. QGUI application is something new to Qt5. It sits in between the QCore application and the Q application that were present in Qt4, and it's used for when you want a graphical user interface but you don't need or want widgets. Okay, it does not pull in the QtWidgets module or the library, so you save yourself a whole lot of loading time and memory usage for that library. It does, however, still allow us to use QtQuick 2 and also OpenGL. Window here is a custom class we'll have a look at in a second. So we just create a window, we show it, we enter the event loop. Bog standard Qt-based application. Our window inherits from something called QWindow. This again is something new in Qt5. It represents, as it says on the tin, a window. It is kind of analogous to what a top-level widget was in Qt4. It's a drawing surface without a parent, so it will appear as a top-level window on your system, be it on BB10, where it will have no decoration. On Windows, Linux, OS X, it will get the usual window decorations. QWindow is the front-end user visible class. On the back end, as with many classes in Qt now, there is a QPA version of it, the back-end platform-specific implementation. So in the QPA plugin, there will be a class inheriting from QPlatform window. That pattern is repeated all the way throughout QPA. You have a front-end class, which is Q something or other. The back-end one will be called QPlatform something or other. And then in the QPA plugin for your particular system, it will inherit from that. So on QNX, it will be QQNX window, which will be our implementation of the QPlatform window, and that will go off and help us create the actual platform-specific surface on which we can draw. So inside window, we can override the usual event handlers. So here we've just overridden the key press event. Inside there, we're just handling the escape key to quit the application. Nothing fancy. We then have OpenGL Context. So the window is our piece of paper. The OpenGL Context is our bunch of tools we're drawing with. We need both to be able to do things with OpenGL. And again, this is backed in the QPA plugin with a QPlatform OpenGL Context derived class. And that's done for all of the available platforms. So that's OS X, Windows, Linux, which is XCB, and also EGLFS, which is a simple plugin to allow you to do full screen OpenGL based applications. On embedded Linux, there's BlackBerry, soon to be iOS, and Android. And they will all do their platform specific work when you create an OpenGL context. And as I said earlier, if you're in my earlier talk, doing that alone is worth using Qt. Okay, just creating a context on Windows or Linux or Mac is a pain in the backside. Right. So some other classes we have. OpenGL Buffer. Again, I apologize for the repeats of the guys who were in my earlier talk. Difficult to do 2 talks on OpenGL without mentioning these classes twice. OpenGL Buffer. This is just a block of memory. But it's a special block of memory in that it's managed by OpenGL. We create an OpenGL Buffer instance of that class, and then at some point later we can call create on it. And it's not until that point does OpenGL actually get told to go off and allocate some memory. Well, in actual fact, it just creates a handle for that object at that stage. So we've got a handle for an object, which is all wrapped up in OpenGL Buffer for us. And inside that buffer, we can store pretty much anything we like. Typically, this will be per vertex data. So positions, normals, colors, temperatures, texture coordinates, whatever. It has a whole bunch of hints we can pass through it to tell it how we want to use it. So we saw one earlier, but I will show again now. We've got a function called setUsagePattern. And this one is using static draw, which means it's an instruction for OpenGL. It's quite likely to store this buffer object actually in GPU RAM, which means the GPU can access it very quickly without having to wait for the relatively slow PCI Express bus to transfer anything from the CPU side. There's a whole bunch of others. So if we go through to the enum for that, we've got things like stream draw, stream copy, static draw, dynamic draw. Basically, static draw means it's not going to change very much. Okay, you can change it now and again, but if you end up changing it a lot, then the driver is going to be a bit cross with you because it's got to keep copying it back from the GPU back to the CPU side for you to change it, and then back again. Dynamic draw, and the other dynamic ones, are the next step up. They mean you're going to be changing it perhaps every 2, 3, every few frames. So the driver knows, yeah, okay, it's going to stay the same for a little while. I can do some optimizations, but yeah, that guy's going to need access to it again not too long from now. And the stream ones basically mean I can't make any promises. I might change this every frame if I feel like it. Okay. This is for your highly dynamic data. So if you're passing across arrays for matrices like this would be typically things like your bone matrices for your skinning palettes and things. Or if you're using transform feedback objects, then using the stream hints would be much more useful for that. Transform feedback objects, as an aside, what you can do is you can render geometry, you can turn off the rasterization stage, and your geometry goes through the Vertex Shader, and you redirect it back out to a buffer. So you're only running it through part of the pipeline. That means you can use your Vertex Shader to do nice things like calculate new particle positions, for example. So you can have your entire particle engine running on the GPU. Okay? Very, very nice thing to do. A little bit tricky to do at the moment, but very, very handy. Where were we? QOpenGL Shader program. This is essentially the encapsulation of the entire OpenGL rendering pipeline. It fills in the missing bits. Okay, in the new programmable pipeline, there are some fixed stages and there are some programmable stages. So fixed ones are things like primitive assembly, clipping, rasterization, and there's some other fixed tests at the end of the pipeline. Also, vertex pulling is relatively fixed at the moment. For programmable stages, QOpenGL Shader program currently only supports vertex shaders and fragment shaders. There's a little bit of a mismatch at the moment in that QGL shader program, which is the equivalent class for this from Qt4, which is still in Qt5, but in an add-on module, also supports geometry shaders. Geometry shaders were disabled in the development of Qt5 because it required some other API hidden away in the widgets module, which didn't make it into QtGUI, and we noticed too late before we could change the API before 5.0, so geometry shaders will be re-enabled for Qt 5.1. There's already a patch on Gerrit you can get to do that if you need it now. So we can have vertex shaders and fragment shaders with a little bit of extra effort geometry shaders as well. Additional shaders we could put in there in the future are tessellation shaders and compute shaders. Tessellation shaders are very, very nice. Okay, if you're rendering geometry, what it allows you to do is send through your vertices as something called a patch primitive, which is anything you want it to be. Okay, a patch is the primitive, is the prostitute of the GL primitives. Okay, it's whatever you want it to be. Basically, you send through a patch. It could be just a series of points, in which case one thing you could do is you could reinterpret those points as positions of sprites, and then in your tessellation and or geometry shader you can convert those points into quads, okay, or 2 triangles. So then all you've done is you've taken your whole bunch of points, you've generated some quads, they get through to the fragment shader, you do a texture lookup, and you've got yourself a very nice point sprite. In fact, they're very much more powerful than the standard built-in point sprites, because you can do things like make them smaller when they get further away from the camera. Okay, you can do whatever you like with them. Other things you can do with the tessellation shader are things like dynamic geometry tessellation for terrain. So you can pass in a let me think about this, which would be the best way to do it. A vertex buffer object with height data in it as your input data. In your tessellation shader, sorry, I got that back to front. You pass in a flat grid of points. You get your height data from some other source. It could be another VBO, it could be a texture. In your tessellation shader, you can basically say, I want to offset this patch by whatever the height is, and I want to tessellate it very, very highly when it's close to the camera, or if it's far away from the camera, I only want to tessellate it a little bit. You have to be a little bit careful about how you do that. So the typical technique that's used is you have your straight edge of the square, you fit a sphere around it, and then you see what size that sphere would be on your screen and tessellate according to that. If you didn't use the approach with the sphere, then your lines that go across the screen would be tessellated correctly, but your lines that are going away from you on the screen would have horrible tessellation, and you'd get all sorts of cracks and artifacts appearing. So bounding it with a sphere really helps to do that method. Right, that's that. QOpenGL Vertex Array Object is a class that's not in Qt yet. Okay, hopefully that will come in Qt 5.1. This is just a very, very thin wrapper around vertex array objects. What's a vertex array object? A vertex array object is essentially a list of references to QOpenGL buffers, and it allows you to switch between them very, very efficiently. So when you're drawing an object, you might have a buffer object for your positions, a buffer object for normals, a buffer object for colors, and so on and so forth. When you want to draw it, you would normally have to make each of those active, enable that state, enable that attribute in your shader, and then draw it. The vertex array object does all that state setting for you in one foul swoop. So it's a very handy thing to have if you're changing between vertex buffer objects a lot. Okay. The other class, which I don't think I have in this example, let me see if I've got another one there with it. No, I haven't, damn. There's another very handy class called QOpenGL Frame Buffer Object. Clues in the name. It represents a frame buffer object. Instead of rendering to the screen, we can create a frame buffer object. We render into our frame buffer object, and then typically what you would do is have a texture attached to that frame buffer object, and then you can re-render again using that texture. And all you have to do is usually render a quad and map that texture to it, and you can process it however you like. And that is exactly what happens inside QtQuick 2. So in QtQuick 2, where you have an item, you render it using your usual QML awesome skills, and then you have a shader effect attached to it. What happens is your item gets rendered into an FBO, the shader effect gets run on that FBO, and what you see on the screen as a result of that 2-pass rendering. So there's just a quick overview of the pipeline, which we saw earlier for those of you who are in the room. So on the CPU side is where we start off with all our data. We make vertex buffer objects, or QOpenGL buffers. We feed it into the vertex shader. It does some transformations. The resulting vertices then get clipped to the screen, and it assembles groups of vertices into primitives, i.e. more than likely triangles. They get rasterized and interpolated, fed into the fragment shader. That does calculations. If those fragments all survive the various tests, then they end up as a pixel on the screen. So the typical application you'll have for OpenGL will be something like this. The application will create a window in an OpenGL context, either yourself, or you do it via something like QGL widget, which will create the context for you, and the window obviously because it's a widget. Or you can use QtQuick view, which we'll see shortly. That also creates a context for you. We create our per vertex data, feed it through OpenGL pipeline, set everything up ready in a row, call a draw function, and the drawing carries on asynchronously. We then are free to go away, update the rest of our application state. Okay, shaders have interfaces. So what we see here is the application side. We have our vertex buffer objects, and then next in line we have our vertex shader, and in there we see it takes in a vertex attribute called vertex position. That's fine, and it also takes in something called vertex color. So our application is responsible for setting up that link between our vertex buffer objects and our vertex shader interface. Just to quickly show you the vertex shader interface. It's this part up the top here. Okay, all the bit before our main function in our shader. So there we can see we're taking in 2 vertex attributes and we're outputting 1. So we're taking in the position and the color and we're outputting a color. This is a very trivial one. The actual shader itself just passes through the color, and as always we have to calculate the GL_position variable. So back to our diagram. So our shader interface is vertex position and color, as we saw, and the output is the out color, and it also outputs the GL_position. They feed into the fixed function pipeline, get rasterized and interpolated. So all of our output attributes also get interpolated, and they feed into the matching interface in the fragment shader. The coordinates in the fragment shader are available as GLFrag coordinate. Where are we? So our inputs to the fragment shader must match the outputs from the vertex shader. And the output from the fragment shader, we can call it whatever we like nowadays, in this case frag color. Shaders can have constants, that's no big deal. They can also have per vertex attributes, as we've just seen, but they can also have something in between, which is something called a uniform. Now a uniform is something that varies once per draw call. So wherever we call GLdraw something in our application, all the primitives that are drawn with that draw call will take on the same value of that uniform. Let me just see if I can find an example. So in our shaders, let me find a more interesting one. We have some uniforms, and we declare it with the uniform keyword, and we can nest them in structs as well if we like, that's no problem. And basically what we have to do is pass in the value for those uniforms from the application. And from the application we do that with OpenGL Shader program. And it's done with OpenGL Shader program set uniform value. So what we do is we pass in the name of the variable, and OpenGL Shader program will take care of going into OpenGL, asking OpenGL what location in our interface does that variable occur at, and it will set the value for us. And there are overloads for loads of different types of values. Okay, so QVector4D, QMatrix, whatever. You can pass in nearly anything you like from Qt to there. Go, next page. Okay, in Qt, I mentioned a little while ago we've got QGL shader program and OpenGL shader program. All of the QGL classes, to clear up some confusion, it was mentioned yesterday in the keynotes that the QGL classes are deprecated. Okay, that doesn't mean don't use them. What it means is they are now no longer part of Qt GUI, they are now in their own standalone module. They're part of the Qt OpenGL module. That has a dependency on Qt widgets. So if you're still using QGL widget, it's perfectly fine to carry on using QGL shader program and friends. For every QGL class, there's a Qt OpenGL equivalent now inside Qt GUI. And if you actually look at the implementation of Qt OpenGL Context, inside it you will find, if you look at the implementation of QtGL Context, inside it you will find a pointer to the Qt OpenGL Context. So all that mapping from the widget-based world back to the Qt GUI world nowadays has already been done. So rule of thumb, prefer the Qt OpenGL classes in new code, because the old QGL classes won't see many more improvements, but you can still quite happily use them. They're not going to disappear. They're not going to suddenly break. Okay, it's fine. QtQuick 2. It's built on top of OpenGL. Surprise, surprise. Everyone knows that. Inside Qt 4 and also in Qt 5 with the QtQuick 1 technology, we use something called QDeclarative Okay, in your application you have your main function, you create a QDeclarative view, you load your QML file, you enter the event loop, away you go. In QtQuick 2, same sort of system applies, you just create a QtQuick view instead. It's dead easy. Can we integrate stuff between OpenGL and QtQuick 2? Well, yes we can in many, many ways. We're going to have a look at how to do it via an underlay. But just as so you're aware, you can do it as overlays. We can do it via frame buffer objects if you're composing your own scene elsewhere. And as I'm sure you're aware, you can make your custom QtQuick items. You inherit from QtQuick item or QtQuick painted item. And inside there you can either use raw OpenGL or QPainter respectively. And if you haven't seen it yet, I highly recommend you have a look at the Qt graphical effects module. Inside that there's a whole bunch of pre-canned effects that use OpenGL shaders which you can drop straight into your QtQuick scenes. Okay, I think it's the only module in the Qt 5 repo at the moment that's written entirely in QML. There's no C++ in there at all. It's purely QML. So let's see how we can go about integrating some of our OpenGL stuff into QtQuick 2. So let me open the example. QtQuick 2 integration. Oh, nuts. Get on there. What have we got? In our main application, we have a Q. Hey, it's gone to the wrong one. Sorry. We have a Q application. This particular case, it could actually be a Q GUI application, unless you're wanting to use textures and things, in which case there's some nice convenience functions still in the Q OpenGL module, which has a widget dependency, which unfortunately we have to put in this case, I believe. Okay, we have a window, which we'll see in this case is actually now inheriting from QtQuick view. So we've replaced our Q window with the QtQuick view. QtQuick view inherits from QtQuick window, and it contains all the nice things like the QtQuick engine, all the context, the scene graph stuff, all of that lovely business that makes QtQuick 2 work very nicely. Inside here, we've put in a pointer to our scene class. This is where we're going to do our OpenGL drawing. And then we've just got a simple QTime object so we can know how to update properly. There's a couple of steps that are useful to do. The first one is we call set clear before rendering to false. That means we are responsible for clearing the screen if we want to. If you're rendering something that likes to have the previous screen there, then you don't have to clear it if you don't want to. But the key thing to making this work in combining OpenGL with QtQuick 2 as an underlay is this guy here, this signal. This is a signal on QtQuick view or QtQuick window, I can't recall which, but it's a signal that gets emitted just before QtQuick 2 wants to render all its own scene. So what we do is we connect that signal to a slot of our own. Let me put on another line. And in our case, we're going to call it render OpenGL scene. You have to be a little bit careful with this slot, or this connect statement. Where does QtQuick 2 render its own scene? In which thread? Okay, we've got a separate thread. Any other takers on that? It depends. Always depends. Okay, and it depends on what the QPA platform tells it can do. Okay, on OS X and BB10, yes, it happens in a separate thread. On XCB, it may happen in the same thread, it may happen in a separate thread. So you have to be a little bit careful, and you have to be aware of which thread you're going to be rendering your call in. So since we're going to be borrowing the OpenGL context from the QtQuick 2, then what we have to do is make sure we operate in the same thread as that context. So what we would normally have to do is be explicit and specify Qt direct connection in there. Okay? If you do that, then your slot is guaranteed to be called in whatever thread context QtQuick 2 is using. So just be aware of that. In this particular case, I know it's single-threaded because I'm on the XCB platform and I've explicitly disabled it from using multi-threading. So I can just remove that for now. Okay, but just be aware to put that in. So in our render OpenGL scene, all we do is we have a simple static bool. We check to see if this is the first time we've come in here, and we call our own initialize function and a resize function just to make sure we're set up ready to go. So inside initialize, no, it's just gone to the base class. Inside initialize, this is where we would build our shader program, prepare all our vertex geometry, so on and so forth. Okay, I won't bore you with all the details again. It's just the same hello triangle thing we saw earlier. And then once we've done our initialization, we can just call our own render function. Inside our render function, oh, I've done it again. Apologies. Inside our render function, we do eventually get around to clearing the screen ourselves. We bind the shader program. We use a vertex array object to help us set all the state quickly. And we call GLdraw arrays to draw some triangles. That's just what we had in the pure OpenGL case. However, we are borrowing somebody else's context now. Okay? So just like when you go to the lavatory, it's very nice to be neat and clean. Leave it how you left it. This is what we have to do in this case as well. So we release or unbind our vertex array object. Okay, this takes care of making sure none of our vertex buffer objects are still bound. If they are, QtQuick 2 won't be happy. Okay, it won't draw anything. I sat there for ages a couple of weeks ago staring at a blank screen wondering why, and that was why. And we also unbind the shader program. Okay, so at that point we've returned the OpenGL context to how we found it. Now, when execution returns from our slot, remember, which has been called from QtQuick, the context is in exactly the right state that QtQuick 2 expects, and it can carry on and render the scene. So let's just run that. So here is our lovely triangle that we had before, and we've now got a QtQuick 2 scene sitting on top of it. Okay, so all we've done is we've created a QtQuick view, inherited from it. We've set a QML file on it. We're rendering our own scene in response to when QtQuick tells us. Okay, that's not particularly exciting. It's just a triangle with a scene over the top of it we can ping a square around. Woo. But that's the basic integration. Yes?
Can you go back to that example?
Sure.
You using like the plain vanilla OpenGL functions here. Is there a way to use the Qt provided abstractions for that rather? In that case?
You mean GLdraw arrays?
Yes.
Yep. There is no Qt abstraction for GLdraw arrays. Okay. However, there will be in Qt 5.1 a set of classes, hopefully, which do provide an object with all the functions for that particular version of OpenGL available. That's very nice because then you'll get compile time errors if you use something that's not in that version or that profile. If you're interested, I can give you the link to the patch for that after the talk. Okay, so that's the basic integration, not too difficult. What else can we do? We can update our scene. Okay, so now we can get some small amount of animation into our scene. So we've still got the same QtQuick 2 user interface over the top. Oh yeah, notice as well that this triangle is not fully opaque, so our QtQuick 2 UI is being nicely blended over the top of our OpenGL scene. How do we do this? Again, the answer is absolutely trivial. If I find the right file. As now, we create our own timer. So we're creating a QTimer object, and we're hooking up its timeout signal to a slot we are imaginatively calling update, and then we start it, and to run every 16 milliseconds. We've got our render OpenGL scene as before. We're connecting up to the before rendering signal just as we did before. And inside our update function, we calculate the elapsed time from the last frame, and we call the update function on our scene. Inside the update function, no, it's done it again. Stop doing that. Inside the update function, all we do is we modify a simple rotation matrix. Trivial. Okay, we're not modifying any OpenGL state in there whatsoever. Once we've done that, we call QQuickView update. That sends a message to the QQuick2, we want to redraw the scene please. That will then in turn emit the signal which says before rendering, and it will do so when QQuick2 is ready to do it, and then we end up in our slot and we redraw the scene. So we've updated our internal state, told QQuick2 something's changed, we want to redraw, it goes ahead and does it by calling that function.
Where does the 16 come from? 60 frames?
It's just 16 milliseconds, 60 frames a second. It's just 1000 divided by 60. Okay? Nothing special. No, it's a very, very simple update mechanism. I'm not trying to be clever here. This is just simply for illustrative purposes. Okay? Normally we do something a bit more elaborate than this.
Is there a way to synchronize with the QML animation timing?
Is there a way to synchronize the QML animation timing?
Is there a frame rendering signal as well?
Well, that's what this before rendering signal does. It will emit whenever QML wants to re-render. So you'll render whenever QML wants to and whenever you ask it to. Okay? But whether it's v-synced is dependent upon your platform. Okay? I can't remember what the API is for setting that. Thomas, do you know? No, I can't remember. I know the QPA plugin has an abstraction for refresh rate. And I can't remember exactly where the vsync comes in. I'd have to look it up afterwards. Sorry, question? Yeah.
Do you still need to connect the before rendering
Well, the requests for the updates can come from two places. They can come from QtQuick2, or they can come from us. So the timer is our trigger for updates. QtQuick2 has its own animation timer. Okay, so that signal catches the QtQuick2 source. So that's what we have to do. We don't clear, or we request not to be cleared. We get the notification via that before rendering signal. We borrow the OpenGL context. We don't have to create our own. We set the state, draw stuff, and we reset the state to what QtQuick2 wants. If you don't do that, your QtQuick2 scene won't appear. You'll just see your stuff, hopefully. So that's the rules of thumb that I've found so far for what needs to be reset. Unfortunately, that's not documented yet. Okay, with the QGL paint engine in Qt4, we had a begin native painting and end native painting pair of functions that did that kind of stuff for us. There's discussions going on at the moment whether we need something similar for QtQuick 2. Okay, that would make this kind of stuff a little bit easier. Okay, QtQuick 2 uses OpenGL 2. Sometimes we want to do more fancy stuff that uses newer versions of OpenGL. Can we do that? Yes, we can. What we have to be aware of, though, is that we have to use a compatibility profile context. That means we still need all the old fixed function stuff to be available. I'm not sure exactly what inside QtQuick 2 is using it, but something is. I tried it with a core profile and got zip. So we have to use a compatibility profile rather than core, but other than that, that's it. We can customize whether we want multi-sampling, we can customize the depth buffer size, we can customize the color depth buffer sizes. So just to see how to do that, where's it gone? Very, very simple. Inside our constructor for our window, which is still inheriting QtQuick view, towards the end of our constructor, we create a QSurfaceFormat object. Inside there, we can specify the properties for our context that we want. So here we're asking for OpenGL 3.3. And as I say, we needed a compatibility profile. But if you want to turn on multi-sampling for your QtQuick 2 scene, which by now is disabled by default, okay, that's a fairly recent change, then you can do format dot set samples 4, for example, if you want 4-way multi-sampling. Multi-sampling was disabled for QtQuick 2 for a performance increase and to use less memory because it really is memory hungry. But that's a quick way to re-enable it. So you create QSurfaceFormat, set the properties you want, and then just call setFormat. Deep in its bowels, QtQuick view actually inherits from QWindow, so we just do this exactly as we would for a normal QWindow. When QtQuick 2 instantiates itself and it builds up the scene graph and stuff, it asks for the format from the window, and it creates the context based on what you asked for. Okay, so if your system supports OpenGL 3.3 with 4-way multi-sampling, that's the context you'll get. So then you're free to go away and use those new features. So, very boring example again, but we're using a new context now. But we could now go off and use geometry shaders and instance rendering and all that kind of lovely stuff. And in fact, QtQuick 2 UI. We can do exactly that. So here we've got a scene rendered with OpenGL 3.3, and we're doing some nice stuff with bump mapping and things. We can move cameras away and closer and rotate it. And the animated text that's falling down from the top and exploding out is all done using QtQuick 2. That's just a simple text element, and we're animating it, changing properties for the character spacing, and away it goes. So we're nicely composing our own scene using QtQuick 2 over the top. That's nice. Press F1, then we get some settings pop up. Okay, so now we've got a nice little UI we can very easily lay over the top of our OpenGL scene. So imagine you had medical devices or whatever. You can compose your difficult graphs and things in raw OpenGL, your fancy stuff, and you can very easily overlay QtQuick UI over the top using exactly the integration method we've just seen. So we can, pause and start animation. We can adjust the animation speed. So all we're doing here is using the usual QtQuick 2 methods to expose properties. Where's it gone? Sorry, in our scene. So in our scene, I've just made it inherit from QObject as well, and I've just given it a single property called rotation speed. So that's just the usual bog standard property stuff, nothing special there at all. Inside our scene's update function, it uses the rotation speed to update the angle of rotation, just trivial stuff. And then inside our main function, we are just setting or exporting our scene object from C++ out to QML. Okay, that's just the stuff we all know and love, day-to-day bread and butter stuff. So we set that as a context property. We're loading the QML file, and away we go. So let's have a look at the QML file. So inside here we've got our text for the F1 show hide setting stuff. We've got our falling down text, that's just a simple text element, and then that's controlled with this sequential animation that just makes it fall down and then explode out. So if you want to make that text explode out, by the way, the property you want is font.letter spacing. You can get some quite nice, smoothly animated text effects with that stuff now. It's pretty cool. And then we've just got a custom checkbox item and a custom slider control. And inside there we just put on checked and we update our properties of our scene object. Okay? Nothing particularly difficult there at all. So, but we're integrating QtQuick 2, the Qt property system, OpenGL rendering, and the way we control our rendering from our member variables. That's good. We can go better. Oops, wrong button. We can use those properties to update uniforms in our shaders. And then we can really go to town. So let's run that one. Okay, so if you were in my talk earlier, you saw this guy. This is using instance rendering to render 10,000 points in one function call and a nice smoothly animated background with one other OpenGL function call. Over on top of that, we're overlaying our simple OpenGL scene with our show hide settings, the falling text. The settings dialog now is a little bit more complete. But what we can do is use this to do some cool stuff. So we can simply use it to pause the updates. So now the updates of the wibbly function in the background have all stopped. That's simple, yeah, that's obvious how we can do that. We can change the frequency of them, again, so they update quicker. Oops, missed it. Okay, let's set that down there. We can change the spatial frequency, for example, so we get much higher number of oscillations in space. But then we can do some more interesting things. If I change this scale function, if you look at the nicely slow animated blue background, if we change the scale, then that changes the level of complexity of that background. Okay, that level of complexity is coming from a uniform variable fed into a shader that's doing a very simple calculation with a Perlin noise function. And similarly, if we can change some of the other ones, we can make it go much quicker. So now it looks a bit more like fire rather than just some slowly animating liquidy thingy. And we can modify some other uniform variables to completely change the color. So you can change your OpenGL scenes very nicely via Qt properties and via uniform variables. Okay, binding uniform variables in your shaders to Qt properties, exposing those to QML via some object or type allows you to really do some cool stuff. Okay, the QML file for this is trivial. It's just the bog standard stuff. I mean, the user interface, okay, we've got a custom checkbox thing there, a custom slider I stole from one of the existing Qt examples, and a rounded rectangle and a few bits of text. Okay, it took about 30 minutes to just put the whole thing together. It really is trivial. So in our application, what have we got? Let's have a look at our shaders first. Where did it go? That one. So let's have a look at our nicely shaded background shaders. So for our background, our Vertex shader is absolutely trivial. All we're doing is we are passing in vertex positions. Okay? Simple, easy peasy. And just to give you a clue or an idea as to what this shape actually is for the background, if I was to just pull out the camera backwards, we see it's just a sphere. Okay? I've just untied it from the camera so it doesn't move with it. It's a sphere we can move in and out of. So all the geometry we're passing through for that lovely background is just a few points that make up a sphere. In our shader, we're outputting some texture coordinates. That's all we're outputting. We're calculating our texture coordinates on the fly, and we're doing it by scaling our vertex position, x, y, and z, by something called TET-coord scale. And TET-coord scale is a uniform float, which is defaulted to 2. We can set that from our application. Inside our application, what we do, fairly obviously, if you haven't guessed already, is we expose that as a property. So we've just called that scale in our properties here. That's just a single float, and then we can expose our object to QML. Inside our render function, somewhere down here, we will set scale, TET-coord scale. There we go. So we use our set uniform value, TET-coord scale. We determine how we control the generation of our texture coordinates to feed through to the later stages of our pipeline. And then in the fragment shader, just to show you that very briefly, we have a very simple main function. It calls a standard function you can download off the internet called snoise, which generates an octave of Perlin noise. We generate 4 octaves of that, and we use increasing frequencies. We add them up together with decreasing weights, and we use our color bias, which is another uniform. That's what those 3 red, green, blue sliders at the bottom adjusted. And we just generate a fragment color based on that noise function. So we can use those uniforms to adjust the color bias. We can use it to adjust the time, aspect. We can use it to adjust texture coordinates, scale, all these sorts of things. So if you're doing embedded devices where you want QtQuick 2 UIs overlaid on top of some custom OpenGL rendering, so medical devices, radar, systems, in-car infotainment type things, with sort of proper three-dimensional cluster gauges and all sorts of lovely stuff, then this approach is really, really nice. Okay, so very, very minimal amount of work for you guys to do. You've got your OpenGL stuff, you've got your QtQuick stuff. You tie them together just by connecting to that one signal, and you can hook up your uniforms, export those to QML, job done. Okay, thank you very much. Any questions?
So thank you for showing us how to have the OpenGL scene as the underlay. Is it also possible to have a tighter connection, like having the OpenGL scene as an item within the QML scene, which might be a buffer in the OpenGL scene again?
Yeah, I don't have an example with me, but yes, you can render, there's a few ways to do it. You can render your entire scene to essentially a texture. Okay, so that's one way to do it, and then you can use that texture in your custom item. So you would inherit from QtQuick view and implement your paint function there and just essentially render a quad with your texture. So that's a simple way to do it. Another way to do it would be to actually write a custom item, and inside the paint event of that item, do your custom rendering in there. I've not tested thoroughly yet the exact limits of what you can do in there, because you're in the middle of how QtQuick 2 renders. Okay, so if you're doing things like disabling depth rights and all that kind of stuff, you may have to be a little bit careful about how you return that context state again. But there's helpful classes in the scene graph like geometry and other classes that very nicely help you manage collections of vertex buffer objects and things. So well worth having a look at the API for that. So QtQuick item is the main point of entry you want to have a look at. Yes. I will do my best to make them available. Okay, all of the slides and presentations should be available online as videos afterwards, but yeah, I'll try to make the examples available. Sorry, say again?
What happens if your scene does not render fast enough, so you get below 60 frames per second?
Correct, yeah. You shouldn't do too much stuff. Okay? You're working in the same thread as QtQuick 2 in this particular approach. Okay? If you're really doing stuff that is going to be slow, then it might be much better to use your own context in a separate thread and render it to a frame buffer object that is shared with the QtQuick 2 context, and use the texture-based approach I mentioned a second ago. That way then you can render your own speed, and QtQuick 2 will only see your frame updates whenever they become available to the texture.
Just because I'm not sure if I use QGL widget now, and I want to go to QOpenGL, is there a QOpenGL widget, or do I just take a QWidget and a QOpenGL context?
Just carry on using QGL widget. Okay. You can use QOpenGL Shader program, QOpenGL buffer, all perfectly happily with QGL widget. The reason is, if you look into the implementation of QGL widget, that contains a QGL context. Inside QGL context, hidden away inside the private class, you will find a pointer to QOpenGL context. Okay, so they all use exactly the same stuff under the hood, just that the QGL stuff is kept around for backwards source compatibility. This is part of this 99% source compatibility promise Lars mentioned yesterday. So it's not going to disappear, but the QGL classes won't see new features. But you can quite happily mix and match with the QOpenGL classes. Okay?
Got time for one more question?
No, thank you very much.
Thanks, Sean. Thank you.